me over here, I accelerate an electron through some potential difference, delta V. It picks up some velocity, right? It gets some kinetic energy at this point in time. This was all a problem that we did. W equals Q delta V. That's kinetic energy equals Q delta V. That's 1/2 mv final squared because we assumed the initial was 0. You have this problem in your notes from top 5. Q delta V, and we were able to solve the final velocity of that electron flying straight. We discussed momentum and why it doesn't actually shift to TV's locations, because momentum is so small that collision still at that time because the electron has such a small mass, and so on, so on, so on. All right. Now, so that's fine. The electron comes out with this speed, right? In this problem, though, don't worry about that. I'm going to give you the velocity that it comes out with. The velocity that this electron comes out with, going towards the screen, straight towards it, is going to be 3.2 times 10 to the 5th meters per second. Okay. Then I'm going to put a couple of large electromagnets here. A couple of large electromagnets. All right. And I'm trying to draw this in 2D, and it's a 3D situation, but we'll get to that. So I got a couple of large electromagnets. All right. I don't tell you which way the field is going. No, excuse me, pointed upwards. Right. So that means you've got souths up here, and norths for all practical purpose down here, right? Thus, I'm getting a nice uniform magnetic field going up, right? With a strength beta equals, where am I? Here we go, 5.8 microtesla. What's micro mean? Merco. Excuse me. Micro, so it should say, switch the C and R. It means times 10, not negative 9, that's nano. Good, times 10 to the negative 6. So 5.8 times 10 to the negative 6. That's good. Okay. Now, I'm asking you, I give you a time, right? I tell you that it takes T equals 1.4 microseconds. I did it again on that probably. If I did it once, I'm going to do it again. Merco, right? Microseconds, 1.4 times 10 to the negative 6 seconds, right? To hit the screen, all right? Where is it going to hit the TV screen? Now, the magnetic field like this. Just thinking about it, what's the direction of the force that this electron is going to experience? Yeah, I got this. It's going to come out of the screen. A magnetic field like this, if you can imagine that this is the TV screen is set up over here, okay? A magnetic field pointing vertically actually causes the electron to come to the side.
Yeah, shouldn't it go that way?
Oh, thank you. It's an electron, negative, so it's going into the screen. Apologize. Good. So this is going to, we already know the force is going into board for our direction, because the left-hand rule, right? Negative opposite direction on that force. So let me draw a different picture here. Right, we got this going on here. Now let me just draw a screen. Okay, so I've got a screen, right? The electrons from this perspective are coming from you to hit the screen, right? Coming from you to hit the screen. The force from that top one is into the board, right? The force from this picture, we're going to say, is to the left. Okay, I'm just drawing a different perspective on this. Right, so this electron is going to, it starts out somewhere here in the center of the screen. I'm shooting it right at the center, right? Okay? Does that make sense? I'm blasting it. I'm standing back here from where Jake's at. I'm shooting electrons at the screen. Yes? The electron is going to curve and hit somewhere over here. Some distance x away. Yeah? Some distance x away from that center where I shot it. Right? Now, I want to know what that distance x is. Okay, I want to know what that distance x is. Now, up here, you have time, right? How can I find this distance x? I'm looking for how far to the left does it hit. What else do I know? I know initial velocity. Now, is that initial, what component of velocity is that then? Is that the to the side components? No, that's the forward components, right? So that velocity, actually, that initial velocity is given, doesn't even play a factor into making it go left and right. What's the initial velocity for the going left and right piece? Okay. 0. But it's going to be accelerated, yeah? It's going to be accelerated to the left. Just a little bit. Everybody see that? It's just the way I drew it. You could say to the right. This is the main picture that we're going with. And what I'm doing is I'm taking this entire picture, right? It would have gone into the board, and I'm swinging the gun and everything out towards you. All right? So into the board then becomes to your left. Does that make sense to everybody? It's like I'm grabbing, I'm taking this piece out there, and this would be the screen, the smart. Okay, so it goes to the left from this other picture down here. The initial velocity is 0. They also give us time. T equals 1.4 times 10 to the negative 6 seconds. Let me talk about where I got that time from. I got that time. I got this time from the velocity. I knew the velocity that's going in with 3.2 times 10 to the 5th. That's the going straight at the screen, and then the screen is 45 centimeters away. So I got the time that it takes the electron to hit just from, I assume that it's pretty much constant velocity. It is in that axis, constant velocity in the straight end. So I got it from V equals S over T. All right. I saw for time it would take if the electron went straight. I know we didn't do projectile motion, otherwise this would make a lot more sense to you. But just because there's a force causing that electron to curve, doesn't make it take any longer to hit that screen. Okay? The velocity going forward, that component of it, always stays the same. Okay? Always stays the same. So I can use that time down here. All right, so I've got how far over to the left is it going to hit? Does everyone understand why my initial velocity is 0? I got a yes, I got a yes. How about the rest of you? No. All right, I got yeses and nos. In projectile motion, or anytime you have a curving path, right? Let me grab a golf ball. I want you to use the Earth's gravity as an example. Right? The Earth's gravity provides the exact same motion as this is going to. Right? I start out with a constant velocity straight forward, right? But then there's a force pulling it downwards. Here the force is pulling it from this bottom perspective to the left. Okay? And what happens? Well, it curves downwards, right? Look at that. But the speed in the, what I have is the x-axis, if I throw it horizontally, is going to remain the same the entire time. What's the initial velocity as soon as it leaves my hand, though, at the y-axis? 0. In fact, let's see if we can work this down. I had another guy in the class who was pretty good at it. Need a volunteer who is good at dropping things on time and throwing things straight across. Come on, come on. Candy, you have been volatile. Come on. Hold this. I want you to pick a location over there that's, no, stay right here. Okay? I want you to pick a location over there, and I need to come over here, right, so you drop it. And I want you to throw it perfectly horizontal, right? On the count. Yes, and don't, make sure, the tendency is going to be to arc it up. Don't arc it up. Straight horizontal when you're letting it fall. Like that. Drop it from the same height. 1, 2, 3. They hit at the same time, right? There's a little bit of air, obviously, for what we're doing. They hit at the exact same time. Do it again. There's no debate that the initial velocity of my golf ball is 0, right? I'm just dropping it, okay? The initial velocity of the y-axis of his golf ball is 0 too. It gets accelerated downwards. All right, here we go. 1.
Wait, we went on 3.
Yeah. 1, 2, 3. 1 hit. It takes the same amount of time. He can throw it as hard as he wants. If he throws it perfectly horizontal, the initial velocity in the y-axis is still, who said? Nothing. 0. It takes the same amount of time for a bullet to hit the ground as if you stood there next to the gun, and that's assuming you fire it horizontally, right? If you stood next to the gun and dropped the bullets. Same amount of time, okay? The initial velocity in the y-axis is 0. So the initial velocity here is 0, okay? The velocity moving it to the left is 0. This force is, instead of moving it down like gravity, the force is moving it to the left. And the initial velocity is all in the beginning, all in the going straight at the screen part. There's a force, right, the magnetic force on this charge, which causes it to pick up speed going to the left, is what moves it, right? But in the beginning, that particle is just going straight. It's not going to the left at all. There's no component of the velocity going to the left. Does that make sense? So those of you who were struggling, which was most of us, right? Do you get that now? Y'all do not have the advantage of having learned projectile motion. I apologize for that. We good with this? Okay. At a time, I have initial velocity. Can I figure out an acceleration? Can I figure out an acceleration for this particle? Ah, good. F equals ma. Right? F equals ma. And the force being applied to this electron is the magnetic force, right? This is QVB equals ma. Does that make sense? Charge of the electron, QV, velocity of the electron, beta, that's the magnetic force. This electron's flying through a magnetic field. QVB equals the mass of the electron times its acceleration. I've got everything except the acceleration. Charge of an electron off your sheet is 1.6 times 10 to the negative 19. Velocity of this electron here is the velocity going straight forward through it, right? That's the, from the previous part. Come back up. 3.2 times 10 to the 5th. Beta, I'm going to need more room. Beta is coming back up. 5.8 times 10 to the negative 6 Tesla. Equals mass of an electron, 9.11, 10 to the negative 31st. That's in your packet. Hey. Okay. Solve for me here. Got acceleration. All right, so we got an acceleration of 3.26 times 10 to the 11th. So now that's this acceleration here, right? 3.26 times 10 to the 11th meters seconds squared. Okay. Now look at your kinematics. I'm looking for x. I know initial velocity, I know time, I know acceleration. Which kinematic equation do you want me to use? V equals, I will define a velocity. S, there we go, yeah. S equals ut plus 1/2 a T squared is exactly what I need to use here. S equals UT plus 1 half AT squared is perfect. That's S equals, what happens to this entire term UT? 0. 0 times anything. 0. It just goes away, leaving me with my 1 half, 3.26, 10 to the 11th, times that time, 1.4, 10 to the negative 6, quantity squared. Get the S. Give me that again, please.
0.32.
0.32 meters. Double check that, please, so everyone get it. 0.32 meters, 32 centimeters. Is that a reasonable answer? Yeah. Yeah, I mean, that's the electron curves. It probably didn't make it all the way to the other side of the screen. That's from the center of the screen, it went, here's a meter stick, 32 centimeters, right? It went 32 centimeters. So the TV must, at minimum, right, be 64. TV must be that wide. That's not an overly large TV, right? That's about a regular size TV that you have. At minimum, it must be 64 centimeters wide. Make sense on this problem?